In this video, we'll be looking at a new and very powerful type of neural network called the transformer. Transformers have completely changed deep learning in the past few years. It's responsible for state-of-the-art results in NLP, and even computer vision and computational biology. This video will be broken down into three main parts. 1. What are some of the amazing accomplishments of transformers? 2. What makes transformers special in the context of deep learning? And 3. How do transformers work? Since transformers are fresh on my mind after having just created a new course, I've decided to make this free video to help you understand the main points. So let's start by discussing some of the amazing accomplishments of transformers. When transformers were first created, they were applied to the task of neural machine translation. For example, translating English into Spanish or vice versa. Transformers were able to achieve state-of-the-art results on this task. As you know, machine translation is part of the broader field of natural language processing. It turns out that transformers were able to beat many benchmarks in NLP, in addition to translation. Transformers are the first machine learning architecture capable of generating long, coherent text that makes logical sense from beginning to end. This is the first time that people have seriously wondered whether or not they would be able to distinguish between a human and a machine in the context of conversations over the internet. In fact, transformers are so good at this, they have even been put into production as a way to automatically write computer code. This is a real product called GitHub Copilot. More recently, transformers have been applied to computer vision as well. One of the most popular architectures is DALL-E 2, which is able to generate amazing art and photorealistic images based only on a text prompt. I encourage you to search for some examples of what it can create, because the results are truly amazing. Yet another application of the transformer architecture has been in computational biology, where they have been used to solve the long-standing problem of protein structure prediction. Since DNA is essentially a programming language, transformers are also a promising technology for the field of genomics. One example of this is DNA-BER, which has been used to achieve state-of-the-art results in genomics tasks. So hopefully you're convinced that transformers are nothing short of amazing. They prove themselves time and time again with impressive results in a wide variety of fields. Now, what makes transformers so special in the context of deep learning? One of the most important inventions in deep learning has been transfer learning. This allows you to take the weights of a model trained for one task and apply them to a new task to achieve better results compared to what you would have gotten if you had just trained a neural network from scratch. Previously, transfer learning had only been applied in the field of computer vision, where models were pre-trained on supervised data, specifically ImageNet. However, this changed with the advent of transformers, which allowed us to apply transfer learning to NLP as well. Moreover, with transformers in NLP, we don't even require supervised data, since the pre-training methods we use allow transformers to learn in a self-supervised manner. This is very good for all of us, especially those who are working alone or on small research teams. The latest transformers cost millions of dollars and weeks of time to train, which most researchers around the world cannot afford. Thanks to larger groups sharing their models with the rest of the world, we can leverage the enormous amount of work others have already done. So the next question you might have is, why do transformers work so well? It all comes down to how transformers actually work. Transformers are neural networks built from the transformer block. Just like we have convolution blocks for CNNs, LSTM blocks for RNNs, so too do we have transformer blocks for transformers. As such, understanding the transformer really comes down to understanding what goes on inside the transformer block. The transformer block is based on the attention mechanism, so once you understand attention, you essentially understand transformers. But to understand attention, it helps to understand RNNs. This makes sense since both RNNs and transformers were originally designed to handle sequential data. So as you recall, RNNs work by sequentially computing a hidden state for every time step of the input sequence. The problem with this process is that computing these hidden states one after another can take a long time. We need to wait for the hidden state at time t to be computed, before we can compute the hidden state at time t+1. Moreover, RNNs are prone to the vanishing gradient problem. RNNs are actually very deep networks, if you consider the time dimension. The distance between the first input vector to the loss is as large as the input sequence itself. As such, RNNs have trouble remembering things from the past, which is why it has trouble generating long sequences of coherent text. Attention works differently. For each hidden state at some particular time t, we compute an attention score for each of the input vectors in the input sequence. This will tell that hidden state how much to pay attention to any particular input. Importantly, all inputs are treated equally, so unlike RNNs, which can't see things very far into the past, attention allows us to see all the inputs with equal clarity. Furthermore, the computation of each hidden state does not depend on the computation of any other hidden state. Therefore, attention can be parallelized in the GPU, making the computation of attention weights very efficient in time. We don't have to wait for any hidden state to be computed before we can compute another. So that's a simple, 3-point summary of transformers. I hope you are just as amazed as I am about the amazing capabilities of this new kind of neural network architecture. Now, this was just a short summary video. There is so much more to learn. Did you know that it's possible to use a transformer in just one line of code these days? You can use state-of-the-art models to do sentiment analysis, named entity recognition, neural machine translation, text summarization, question answering, and zero-shot classification with just a few minutes of effort. This was not the case in the past for any kind of machine learning model. Furthermore, with a bit more effort, you can even learn how to fine-tune transformers on your own custom datasets, so that you can use them for any task you need. Again, the ease with which you can do this is kind of unprecedented. At the same time, I think it's still worth learning about how transformers actually work. In order to apply transformers to new tasks, you can't just use what other people have already built to do things that have already been done. Take, for example, DNA-BERT. In order to train DNA-BERT, you would have had to build your own transformer, load in your own dataset, define your pre-training objective, and train the model just as you would any other neural network using TensorFlow or PyTorch. This, in my opinion, is the most exciting thing about transformers, not just what we have already done, but the possibilities we have yet to achieve. Thanks for listening, and I'll see you in the next lecture.